right, complex numbers revision again. Let z equal to 1 plus 2i. I think these are easy. Can we say these are easy? Anyone having any issues with these in particular?
Sam, when we did complex numbers, we didn't go to here.
We didn't get to here. Of course we did. Z is 1.
I might not be remembering that. It was a while ago.
Okay, that's all right. So then let's do it. Z equals 1 plus 2i. W equals 1 plus I. Find in the form x plus iy. Easy. So Z is 1 plus 2i. W with a conjugate. What does that mean again? 1 minus I. So it just means change the plus sign to a minus sign, right? So 1 minus I, and then of course you just expand this. So 1 times 1 is 1, minus I, plus 2I, minus 2I squared. I squared is -1. -1 times -2 is +2. Plus 1 is 3, and then plus I. 2I minus I. All right, any questions about that one?
That's simple.
Yes. That's funny. 1 plus I. All right, what do we times top and bottom by? Ben, you said it last week.
Yeah.
1 minus I.
Yeah. 1 minus I. 1 minus I. So the top becomes 1 minus I. The bottom, do you know what it becomes just by looking at it? Unless you remember the formula for conjugates.
Well, it was just 1 minus I squared.
Yeah.
So that'll just be 2.
See, usually for rationalizing, it's a difference of 2 squares, isn't it?
Mm-hmm.
For complex conjugates, because your y squared will have an I squared, what will happen is every time you actually expand this, there'll always be a plus instead of it being a difference of 2 squares. So what you can remember, it's always going to be 1 times 1 is 1, and then plus these 2 multipliers, which in this case is 1. And yeah, you're done. 1 minus I over 1 plus 1, which is 2. All good? All right, let's do these ones. On an Argand diagram, shading the region where the inequalities 0 less than real of z less than 2 and this less than or equal to 2 both hold. Anyone remember how to draw the first one or how it works or what it means or anything? 0 less than or equal to real of z less than or equal to 2. It's not hard. Believe me, it's as simple as when Anouk just said here, he's like, oh, is that it? It's exactly the same for this one here. So just don't overthink it and tell me what you think. 0 real of z less than or equal to 2. No idea at all? Anyone? A guess? No, not even a guess. Okay, so real of z, it's just x. So it's just, please draw x between 0 and 2.
Oh, that's what I was going to say.
You didn't say it. You know, I keep trying to tell you guys, you got to say it.
Oh, yeah, but I thought it was a straight line through
0 and 2.
0, 0, 0. Yeah, 0, 0.
It is a straight line. Oh, like you mean vertical, like a yeah, no, it's because x has to be between 0 and 2. So it's any number as long as x is between 0 and 2, which looks like these. What you're saying would look like this. Y. X equals y or y equals x. Then you would draw this one.
Yeah, that's what I mean.
So there it is. There it is. That's that one. Anyone remember what these ones become? What shape they become?
Are they circles?
Yeah, that's good.
That was locust, right?
Yeah, that was locus. Good job.
Okay. The one thing I didn't know.
So, yeah, one thing you can remember. All right, so absolute value of z or modulus of z, if it was less than or equal to 2, that's a center at 0, 0 with radius equal to 2. Not square root of 2, just 2. Now, we don't have it at just there. We've got it at something like this, which is z minus 1 plus I less than or equal to 2. In fact, what we'll do, I'm just going to change this for an x here. What we'll do is I'll prove it again, just to remind you guys on how we prove these. So to prove, you let z equal to x plus iy. That's how we did our locus questions. Unless you can see them, which are a lot easier. So if z was x plus iy, you would get x plus iy minus 1 plus I less than or equal to 2. And then you just group your real and imaginary, and what you're left with would be x minus 1 plus factorize your I out, so y plus 1i less than or equal to 2. That's your real, that's your imaginary. Does someone remember how to find modulus of something? What was the formula for the modulus of something?
Is it a y on x or something? Like.
That's to find the angle.
Oh wait,
It's just Pythagoras.
Pythagoras. Sorry.
Pythag. Square root of x minus 1 squared plus, ringing a bell now, equals 2. Then you get rid of the square root, and you just proved it. Your center is where? 1.
1 negative 1.
Minus 1. Where's your radius?
2.
At 2. Whereas I could look at that and I knew the answer. Why? Because I factorize it out, the negative, 1 minus I. And the idea is whatever you see there is the actual center. So that would be 1 and that would be minus 1. So for complex numbers, they're not the opposites. But if you did do the opposite, you obviously would get it wrong. But then I was going to say you could have just proven it if you forgot, like I just did now, which took me 2 seconds. Center's at 1, minus 1. Now, before I move on here, radius is 2. I need to make sure you guys are still with me and I haven't lost anyone. There's your circle. These are all equal to, that's all equal to. It's less than, which means it'll be inside. And between these, the answer is this. All right. Who remembers it now, or who goes, I don't remember this at all?
Yeah, Sam, I don't remember this.
Yep, at all. Anyone else? At all? Like 0? Like I've completely forgotten all this. I don't even get what you're doing. Or maybe we just have never done it. Anyone else? All good? Otherwise, you guys are like, okay, fair enough. I remember this somewhat. So Mariette, for you, you're like, okay, I think I remember this. Now.
Yeah, I remember the first part a lot better. I can do that.
Yep. And then the second part for the circle?
I can't remember the circle part.
But do you remember these were circles, or you still don't remember that either? So the modulus.
I didn't get that. That was a circle.
Okay. But then when I said let z equal to x plus iy, you understood how to sub it in, and then grouping, and then what about the modulus bit? You understood that? Square root? Yeah. Okay. And look.
Sam, I know the modulus bit, but I don't think we ever did the circles. Like, I never did.
Yep. Could be, because I think, yeah, you were on that Saturday class, so you probably would have changed with extension 1 and stuff. I get it. Okay. So we've got a bit to do for you in Nook over the holidays. C. Yeah, this was a very small rule. Let's see if you guys remember this. It is given that 2 plus I is a root of this. State why 2 minus I is also a root. Does anyone remember why 2 minus I can also be a root?
No.
Was this roots of unity?
Roots of unity? No. No. Give me a second. I'm just going to charge my.
Okay.
I will show you a roots of unity question, just so maybe you can remember what roots of unity were again, which is.
Wait, this is the square root one, right?
Square root.
Where you did like x minus y squared equals Wait, no, that's another thing. Don't worry.
No, hold on.
Okay, don't worry.
Unity. In here, there's unity. Yeah, that question is unity with de Moraes and stuff like that, but not something we're going to look at just now. Back to this one here. If 2 plus I is a root, the idea was as long as your polynomial or anything really has coefficients here that are real. So this is real, R is real because it says it, S is real because it says it, and 20 is real. Therefore, 2 minus I is also a root. So the conjugate is a root. So if x plus iy is a root, then x minus iy is also a root. If and only if the coefficients are real. Do we get that? Yes? If you go back to, I think, week 2 of complex numbers, it's in there. All right, and then it says obviously factorize. So factorize over the real numbers. Well, now you know your 2 roots. So what would your third root be? What do you guys remember from just, I guess, 3-unit polynomials? If you've got 1 root, you've got your second root, what would you let your third root be to start working this out?
Would it be 3?
How did you know it's 3?
Oh, because I times both of them, and then I just did it, and then it gave me 3. I think.
No.
Okay.
I think it's going to give you 5 when you times both of them. But anyways, so if you guys remember this is technically like saying this is alpha, this is beta, and then your third root is gamma. So roots are 2 plus I, 2 minus I, and your third one is, in this case, we're just going to label it as alpha. So your 3 roots are these. All right. Now you also know, does this ring a bell? Roots are, or have we forgotten that as well from 3-unit?
Yeah, this thing, yeah.
Anyone forgotten this? What topic I'm talking about? Mariette, you remember this as well? Azra, all good with this? Roots are 2 plus I, 2 minus I, cool, alpha. And then, so therefore you've got sum of roots. You've got sum of roots 1 at a time, you've got sum of roots 2 at a time, and you've got product of roots. Product of roots would be 2 plus I times 2 minus I times alpha. So 2 times 2 is 4. 4 plus 1 is 5. I think you're meant to say, Ben. So 5 alpha is equal to minus B, C, minus D. And therefore you just worked out what the third root is, which is negative 4. Does that make sense, you guys? The reason why I didn't do these two because they got R's and S's. And it's not going to allow me to find my alpha, my third root. Now it says factorize. What do you usually do when you've solved? If you know your 3 roots, how do we factorize? Don't make it hard. If you now know the 3 roots, that's 1, that's 2, that's 3. So your roots are Z equals 2 plus I, 2 minus I, and negative 4. How do we factorize? Think of basic year 10, year 11 now. You've solved. You want to factorize?
Z minus Z times I, Z minus I, and Z minus 4.
Yeah, I think you had it right. That's it. So you're going to bring them to the other side. So what you're going to do is have z minus 2 minus I. Then the other one would be z minus 2 plus I. And your last one will be z plus 4. Minus 4. The reason why I said it's over the real numbers is because technically this isn't real, is it? This is factorized over the imaginary. So what you've got to do is expand this and simplify that. But factorize, you guys can't forget your basic factorization. And when you've solved, to factorize, just go back to the left-hand side. All right, and then z times z is z squared. I'm just going to expand. Nothing, I'm not doing anything fancy. Minus 2z plus 4 minus 2i minus iz plus 2i minus I squared. And then, if I've done it right, z squared minus 2 is minus 4z. Zi minus zi, sorry, zi minus zi cancels out. Minus 2i plus 2i cancels out. And I'm left with 4 plus 1, which is 5. And then z plus 4. There you go. You just factorized it over, you just factorized this particular polynomial over the real field. And that's how that would look. So a bit of revision that we need to do, isn't there? Prove by induction. Let's try this one. We haven't done induction in a while, and we definitely haven't done induction with complex numbers, but there, you can't say that, because inductions, it's just a proof. You can't say, oh, we've never done induction with complex numbers. It works the same way. And you want to remember what step 1 is?
Proof for n equals 1.
It's actually test for n equals 1. Test true for n equals 1. Test true, n equals 1. Good. So you're going to get, I guess, left-hand side equals cos theta minus I sine theta. Right-hand side, n is 1. So you get cos is theta minus I sine theta. Therefore true. Step 2. What's step 2?
Assume n equals k.
True. N equals k. So therefore you get cos theta minus I sine theta k equals cos k theta minus I sine k theta. And then step 3, prove true for n equals
K plus 1
K
theta.
plus 1.
k plus 1. And then I like to write my i.e. i.e. this is what you're proving. You're proving cos theta minus I sine theta to the power of k plus 1 is equal to cos k plus 1 theta. Whoops. Cos, yeah, I had it right. Cos k plus 1 theta minus I sine k plus 1 theta. All right. Yep, that's it. Okay, so I just replaced it. All right, what do we start with usually after that? So there's your IE. Azra, you would know because...
The actual proof.
No, what's your first line here? What are you going to write now?
Left-hand side equals.
Left-hand side equals, yep. So then that would be cos theta minus I sine theta to the power of k plus 1, right? So left-hand side, because you're going to try to, that's what you're trying to prove. That's why we write the IE. So we're hopefully going to move from here to here. That's our aim. So left-hand side equals this. Well, we know this, using our index laws, is just cos theta minus I sine theta k dot. open bracket, cos theta minus I sine theta. Right? We know that k plus 1 is the same as power of k times the same base to the power of 1. K plus 1. We agree with that? Next line. What do we always do after? The whole point of this is to bring our assumption in. So that is our assumption. So we're going to substitute this value in. Equals cos k theta minus I sine k theta dot. So that whole thing multiplied by cos theta minus I sine theta. Hopefully somehow we can prove this becomes this. Okay. Let's see. Okay. What would you do at this step? Ben, what would you do? You're here now. What are you thinking? You got to get to this right.
I was thinking de Moraes, but I don't know how that's going to work.
Not yet. De Moraes only if you had a power and if it was plus.
Yeah,
If it was cos theta plus I sine theta, and then power of 5, and it becomes cos 5 theta. Whatever. But no, it's not De Moraes. Just what would you do at this step? Like
just expand?
You would probably expand, right? Because you're not sure that is this yet.
Yeah.
You're like, right, first let me expand this. So then you would go, okay, cos theta, cos k theta, minus I sine theta, cos k theta. What did I just do? I times this by this and this by this, yep. So then you're going to write minus I sine k theta times by cos theta plus I squared becomes minus 1, but we'll just write I squared, sine theta sine k theta. Okay, a whole lot of stuff. Now, does anyone know what formula they've used to get to here? Think about it. Okay, think about no, still nothing?
This is the sine A plus B thing.
Yes! Bingo! It is that one. Cos. What's cos A plus B then? Cos A plus B is cos A cos B minus sine A sine B. Right? And there it is. Cos A cos B minus, because you know that becomes minus, sine A sine B. Because when you expand this, isn't this k theta plus theta? Where A is k theta and B is theta. So you're done. You just rewrite the question out. And then isn't this one here sine cos cos sine? Sine cos cos sine with an I in front. And then you just rewrite the question out. So all we really needed to see here was that was expanded, and then you could have written the right hand side. Any questions? So Azra, there you go. I know you've got an induction question test, but even in a 4-unit complex numbers, that's as hard as it gets, really. So hopefully that's good for you. All right. Let's have a look. So these question 3s, if you go to your HSC papers, will be really good revision of your year 11 questions. Year 11 graphing questions. There it is, like 1 on f of x, y squared, absolute value of f of x, absolute value of x. So if you want revision, that question 3s would be your best bet. I just wanted to quickly check if I can. No, that's Aristotle's. Okay. And we're okay. Oh, there it is. A reduction formula. Easy 1 mark, easy 3 marks. Deduce that. That would have been a little bit hard for you guys because you have to know the 10 limits. Fair enough. Isn't the recurrence relation part for I and find I5? See? Look. Imagine you couldn't get I, double I, and triple I. By using the recurrence relation of part double I, here it is, find I5. Okay, well, you know I5 is just I5 plus I3 equals 1 on 5 take away 1, which is 1 on 4. Find I3. I3 is I3 plus I1 equals 1 on 3 take away 1. And you guys know how to find I5 hopefully now. So that would have been the easiest 1 mark. So I don't need you to walk out and go, oh, I couldn't do it. I lost this one as well. Why? Why did you lose that? And then look, and deduce that this occurs. Where do you think they would have subbed in I5 in? Into probably here. So 1 on I5, let's see, 5 plus 1 is 5 plus 1 is 6. 1 on 12 is less than I5. Maybe it wasn't I5, and it would have been, let's see what number that would have been. 2 on 3. What number did you guys have subbed in? Half log 2. Log 2. I'm just trying to see if I can fudge it out for you guys so I can teach you to do things like this. Two. It would have been 2. I2. Nope, I2. Without actually writing anything down, it's a bit tricky. I2. Yeah, I gotta write it down. But anyways, that would have been easy 2 marks because I5, like I say, is simple. You're just using that one. And then the deduce bit, you would have realized one of those ones would have just been substituted into here. And you would have got this particular inequality out. Okay. Can we answer? Yeah, no, not yet. Not yet. All right. And then just before we go, I'll just do these graph ones, just as a bit of revision. Yep. So 1 on f of x. If I had to draw this one, 1 on f of x, I know that intercepts become asymptotes. This side here would look like this. 1 over small is large. 1 over large is small. This is happy, so it's going to become sad at the same point because 1 over -1 is still -1. At 3, it's still going to be at 1. 1 over small is large, 1 over large is small, and that will look like that. Any questions? Pretty easy 2 marks for that one. And hopefully some good revision for year 11. If you need questions, don't say, Sam, where do I get functions, year 11 questions. Go to the extension 2 and do them. Y squared equals f of x. For y squared, what did y squared do? What did y squared do? Anyone remember?
Do all the negative values go up?
Isn't
Wrong.
that positive and negative case?
What do you mean? Tell me.
Satisfied.
So, wait, Rosemary, what do you mean by that?
So you square root it and then it's just,
Yeah, I agree with that, but
it's positive and negative as well
yeah, but of what?
of the square root.
And how do we draw the square root? You're right. You're getting there.
What?
Say that again.
A circle?
Circle. No. No.
Just like a curve.
It's a sideways
line.
problem.
Yeah, Ben's saying it now. Now look, I just want to get something clear then. So this one here, what did Ben say? Ben said, no, sorry. Who was it that said it? Anuk, sorry. You said this. You said all the negative y values come up. right? Is that what you said? That's this one. Absolute value of f of x. Or even if it was this squared, if it was this side squared, it would be what you also said. The bottom here goes up. So be careful.
Yeah.
The other way around, y squared, is all positive y values right here get reflected down. Now, if it was absolute value of y, it's a straight reflection. So it's just a straight reflection like this. Cool? If it's y squared, you've got to think about it exactly like Rosemary just said. It's a square root, which means it'll be a little bit lower in shape. But I try to teach it to you guys that it's a bit more parabolic in nature. So you can think of y squared as sideways parabolas. So the answer to that would look like this. Give me a second, let me just tell her I'll be there with 2 seconds. And then, let's try this. F of absolute value of x, absolute value, okay, let's try that. Last one. Okay, I would do the absolute value of x first. So absolute value of x, do we remember what to do there?
All the negatives get flipped up.
No, still wrong.
Oh wait, no, it's along the y-axis, right?
All
Wait, am I saying this?
All positive x values get reflected about the y-axis.
Yeah, I got mixed up.
You guys gotta be careful. There it is. That would be f of absolute value of x. And then of course we want to draw absolute value of y. That's when you come back in, and Anouk, and how do we draw that?
All the negative y values flip up.
That's the idea. Oh, well, I think you guys get the rest. There it is. So be careful. As much as it seems like you guys are knowing at least flipping left, right, up, down, whatever, but you haven't perfected it. So instead of getting, I can't say that you guys are you're getting 2 out of 2. It looks like you're getting 1 out of 2 for all of them. So just be careful with that. Really, it's super important that you know which one's left and right, up and down. Otherwise, it's a simple mistake of going this one here. Yep, negatives are gone, or this one here, negatives are gone, or the whole absolute value of negatives gone. Like, it doesn't really work like that. It's important to know sometimes there are positives that are just reflected to the left, or no, the negatives are reflected up, or whatever it is. So it's important to know that. All right. Next week, same thing, 18 minutes, and we'll do more revision. Hopefully, one more time of complex numbers.